Welcome to this video lecture. This is Mark Scythian, FAA licensed aerospace technician, certifications, airframe, power plant, and avionics. Today's date is June 20th, 2016. This video lecture is going to focus on the energy content of common fuels. If we start with gasoline, gasoline contains 20,000 BTU per pound and has a fuel density of 6 pounds per US gallon. Diesel fuel contains 19,300 BTU per pound at a fuel density of 7.1 pounds per US gallon. Kerosene, also known as jet fuel, contains 18,730 BTU per pound at 6.75 pounds per US gallon. And liquid propane contains 21,933 BTU per pound at a fuel density of 4.24 pounds per US gallon. Note that 3.78 liters is equal to 1 US gallon. And also, in regards to octane, in gasoline, octane has no relationship to the amount of energy in gasoline. However, higher the octane grade, the slower the gasoline will burn. So under high compression engines that are not equipped with anti-knock sensing, a higher octane is required on high compression engines to prevent explosion of the gasoline, also known as detonation. But if you have a low compression piston engine, then a lower octane grade should be used. Otherwise, there won't be the compression needed to burn all of the fuel, and a high octane gasoline in a low compression piston engine will just cause you to waste gasoline out the exhaust. I wanted to mention something about octane because octane is sometimes not understood properly, and it is erroneously equated with energy content, but that is actually not true. Gasoline will always have 20,000 BTU per pound with a fuel density of 6 pounds per US gallon, regardless of the octane grade. In terms of BTU output over the function of time, 1 BTU per second is the same as 1,056 watts, which is also equal to 778 foot-pounds per second. 1 BTU per minute output is 17.6 watts, which is equal to 778 foot-pounds per minute. And 1 BTU per hour is equal to 0.293 watts, which is equal to 778 foot-pounds per hour. A BTU is also known as a British thermal unit, which is the equivalent heat required to raise 1 pound of water by 1 degree Fahrenheit. Just like with gas turbine engine compressors, 1 pound of mass airflow will equal 0.24 BTU to raise 1 pound of mass air by 1 degree Fahrenheit. Air having an average density of 0.074 pounds per cubic foot, and water having an average density of 62.4 pounds per cubic foot, respectively. In terms to other mechanical power equivalents, there is 0.737 foot-pounds per second to 1 watt, which is equal to 1 joule per second or 1 Newton meter per second. 550 foot-pounds per second is equal to 1 horsepower. 33,000 foot-pounds per minute is 1 horsepower, and 746 watts is also equal to 1 horsepower. Energy is defined as the capacity to perform physical work. So, with all these variables and energy performance limits of fuels, it's important to match that to the percent brake thermal efficiency, which is the brake horsepower or the usable power output of the engine times 33,000 foot-pounds per minute that quantity divided into the quantity of the pounds per minute fuel consumption times the BTU per pound of the fuel being consumed times 778 foot-pounds per minute. This fraction divided and then multiplied times 100 will yield the percent brake thermal efficiency. And it's important to know there's actually 3 different types of horsepower in any engine or motor. There's the indicated horsepower, which is the total power involved, including the power loss to keep the engine running and overcome friction, compression, and drag losses, plus the usable power that is available by the engine. The brake horsepower is the usable power output available by the engine, and the friction horsepower is the power lost to keep the engine running and overcome compression, friction, and drag. So the brake horsepower is the indicated horsepower minus the friction horsepower. Thanks for watching this video, and have a good night.